Hello, today we're going to talk about rational functions. A rational function is any function that can be written in the form p of x over q of x. And the key here is that both of these p's and q's have to be polynomials. Right? These functions, examples like f of x equaling x to the third minus 2x plus 1 over x squared minus 2x plus 5. Right? This would be an example of a rational function where the top and bottom of the fraction are both polynomials. Right? These are nice because they have nice domains, right? They're defined on really nice parts of the graph. And we can find them, you can say the domains are going to be all real numbers except spots where our denominator is equal to 0. Right? The one thing we can't have is we can't have a fraction that's some number like 5 over 0. Right? I never want that denominator to be 0. All right, let's solve an example of finding the domain of a rational function. Here, the domain can always be thought of as all real numbers except when our denominator is equal to 0, right? Our q of x is equal to 0. In that case, I want to find when 7x or when x squared plus 7x plus 6 is equal to 0, right? We can solve this by factoring. Get x plus 6 and x plus 1. When I solve that, I get x equals negative 6 and negative 1. So our answer, our actual solution, is going to be the domain of all real numbers, right? Negative infinity to infinity, except negative 6 or negative 1. Or one way we can write that is the set of all x such that x is not equal to negative 6 or negative 1, right? We want all the x except the values where x is not equal to, everything except those two things. Okay, let's look at this graph of f of x equals 1 over x, right? This is the simplest rational function we can have. And one thing we want to notice is the shape of the graph is different than maybe we're used to, right? Here we have this vertical line that our function actually never crosses, right? This vertical line has a special name, right? The vertical line x equals 0 can never be crossed by our graph because it's actually a point of discontinuity. If we consider our function f of x equals 1 over x, we can say the domain is going to be where the denominator x is 0. This is a point of discontinuity because it makes our denominator equal to 0. And any vertical line that makes our denominator 0 is what we call a vertical asymptote. So here, if the value a is a 0 of the denominator q of x, then the corresponding vertical line x equals a is going to be a vertical asymptote of the graph. So looking at our original function, since 0 makes the denominator equal to 0, I have this vertical line here that ends up being our vertical asymptote. Another thing I want to notice on this original graph is not only do we have this vertical line I can't cross, but I have this horizontal line I can't cross. So in the same way with vertical lines, we have this horizontal line, which is eventually going to be called an asymptote. And here, similarly, the graph never crosses this horizontal line, y equals 0. And so we call it a horizontal asymptote. But how we find it is a little bit differently. So we say any horizontal line, y equals b, is what we call a horizontal asymptote for our graph if f of x approaches b, right? We consider that arrow to really be the word approaches. As x approaches negative infinity or x approaches infinity. So what does that mean? How do we tell if something approaches infinity? Well, we actually have a nice little theorem that boils everything down. So if we have a rational function, f of x equals these two polynomials, and remember, these are just the common polynomial notation. Here's what we want to do. We want to look at the highest power of x in both the numerator and the denominator. If the power in the denominator is larger than the power in the numerator, then the horizontal line y equals 0 is our horizontal asymptote. If, however, those powers are the same, I have, for example, a 3x to the fourth over a 5x to the fourth, right, plus some other stuff. Right? If those powers are the same, then the horizontal line of their leading coefficients, a to the m over b to the n, is our horizontal asymptote. If, however, the power on the top, the highest power of x in the numerator, is larger than the highest power of x in the denominator, then we have no horizontal asymptote. Okay, let's look at an example of finding asymptotes for a function f of x. So we'll start with vertical asymptotes. If I want to find vertical asymptotes, if we remember, there's spots where our denominator is equal to 0. So we'll say x squared minus 9 is equal to 0. And we can solve this any way we want to. So for example, I'm going to look at this, and I'll just say x squared is equal to 9. And I'll take the square root of both sides. But we want to remember back from earlier, if I take the square root, I'll get a plus or minus square root of 9. Sorry, I got a little bit ahead of myself, which is a plus or minus 3. So my vertical asymptotes are the vertical lines x equals 3 and x equals negative 3. Now let's work on solving our horizontal asymptotes. And even though this may sound more confusing, it's actually a little bit easier to solve. And so what we want to do is we want to look at our function f of x squared equals 2x squared minus 2x minus 4 all over x squared minus 9. And what we want to look for is our highest power of x in the numerator and our highest power of x in the denominator. And what we want to do is remember the theorem from before and say what happens. So in this case, those powers are the same, right? I have an x squared up top and an x squared on the bottom. And so our theorem says if the powers are the same, then I look to their leading coefficients, and that is our horizontal asymptote. So I look for the leading coefficients. Of the numerator, it's 2. And of the denominator, we recall if we don't see 1, we can assume it's going to be 1. So our horizontal asymptote is going to be the horizontal line 2 over 1, or if we simplify that, it's just the line y equals 2. I hope this was helpful, and I will see you all in class.